Okay. So we have this dataset from K TOS, kindly provided by Arthur. So we have a bit we have this function that is in the depth version of .R, and it's still in development, but it's actually just calculating the proportion of the same, what is the proportion of the same genotypes pairwise. And this is implemented in C++, and I was using this specific function to analyze one dataset of 4,000 individuals with 40,000 loci, and it would be millions of pairwise comparisons, and this just takes 2 or 3 minutes to run. And yes, and there are some instructions how to use it and what you should look at to identify the replicates, because as Jillian said, it's very important to, as we are just having our reference population, it's very important first to remove the duplicates so our estimates are more accurate. And then also I compared the results of these functions with the colony that was also done, was also developed by Jillian. This is a great package that uses livelihood, and it has tons of different parameters that you can use, and it's more used for parentage analysis. And so you can set here if there are polygamy in males or in females, but there is a nice output that also identifies the clones in the data sets using livelihood. And so in this exercise, I'm comparing the output of these GL replicates with the output of colony, and we have more or less, I mean, the same, we identify the same clones in the data set. And then, of course, here we can use a bit more, because we are not calculating, or we are not going to calculate heterozygosity, or we are not going to use this data set for structure analysis. We can be more stringent on our filters. We can use a larger, a more stringent call rate, and other more more filters. And the idea is to have around 5 to 10,000 Snips, just the very best. And here we have a Quan cestry, which was the program that was talking about Jillian. Here we first convert our generalized object to the related format, and then we use the package Quan cestry, who has all the 7 different estimates that Jillian was talking about. In this specific example, I'm just using the Wang. Also here we have the implementations in R of Jillian's last program, EMBD9. And then we have another method here that is from the program GC GCTA. And we have also the genomic relationship matrix. And we have also here some methods to visualize all those estimates. And then we have here plotted the 4 different methods. And then we have here a new discovered species in the Amazonas. And we are interested in knowing whether there is multiple paternity within clutches. And we use, here you will see that the PCA doesn't say a lot of things. If we use a genomic relationship matrix, it is also not giving us a lot of information. We use Quan cestry, and we estimate just pairwise relatedness within clutches. And we can see here that we have 3 clutches, and in each clutch, the minimum relatedness value is 0.5. So all the individuals within clutches are siblings. So if there would be a multiple paternity would have siblings, but we don't have. You can do it in your time, and then we have the oryx case, the Arabian oryx that it was is extinct in the wild. In 1972, then we have this program that brought the Arabian oryx in captive breeding, and now we have, after being extinct in the wild, we have now from 5,000 to 7,000 individuals. Here is the story of this project, and relatedness estimates have been very important to guide the breeding program. And you can, yes, also I have some code here to run Sequoia, to also identify parentage, and using the pedigree from to another function to plot the pedigrees, and you can do all this on your time. And then now we have Natasha here. Thank you.